So this is the tropical subseasonal to seasonal tropical map discussion on the 27th of September 2019. And I have a small audience of students from my research group who are participating, and I have a little bit of a problem with my internet service today, so I'm only going to be able to show and discuss figures that I've already downloaded. Luckily, I think the most important ones are here and available for us, and I'll try to get the internet problem fixed for next time. That may cut the discussion a little bit short today. So we're looking at the global sea surface temperature pattern, and there's been some changes from last week, wherein there was a lot of cooling in the West and Central Pacific region that showed up last week that has changed as the westerly wind event, the West Pacific equatorial convective event, has moved off poleward and has left behind a region of relatively light winds along the equator of the Western Pacific, and the sun is able to warm the ocean under those conditions, raising the temperature. It's come up a little bit more just west of the date line than it has in points north of New Guinea, and so it's still resulting in a more Central Pacific El Nino type structure, although the warmest water isn't as far east as it often is in events that get named as Central Pacific El Nino. The big westerly wind event that moved northward and spawned convection in this area is still active in some areas, but moving northward, and it's reduced the sea surface temperatures in this region of the northwestern Pacific. I think last week the warmest water globally was next to the coast of Central America. And so that's changed quite a lot. There's been an exchange, at least the warmest water in the eastern Pacific region has cooled as the active MJO signal has been coming around, and the warm water there is relatively shallow in comparison with other places, so the wind evaporation feedback is enough to reduce the temperature there. And there's been a lot of convective activity over there. The Western Caribbean and the southern and western Gulf of Mexico remain quite warm in comparison with other parts of the world, but now the broadest region of water exceeding this 30 sea level is along and just west of the dateline Central Pacific Ocean. The Indian Ocean is continuing to show a substantial Indian Ocean dipole structure. The warmest water on the north and west, and then the southeastern tropical Indian Ocean is experiencing enhanced upwelling in response to trade winds here interacting with the islands. Excuse me. So we're going to look at the anomalies. Excuse me. It'll be better in a moment. So the Indian Ocean shows a substantial anomalous pattern that is returning to a more canonical Indian Ocean dipole condition. So the upwelling, the most anomalously cold water is right next to the islands, and then extending back to the west. Here, upwelling is enhancing the cooling, while out here, the main source of a cold anomaly is advection of cooler water from the east, but also the wind evaporation feedback due to enhanced trade winds that are responding to the warmer water over here, which is favoring convection in this region more than would otherwise occur this time of the year. I mentioned last time that the relationship between sea surface temperature and convection in the Indian Ocean reverses in the spring relative to the fall, so that in the spring, active rainfall conditions tend to be cool, anomalously cool, because in the spring is the highest sea surface temperatures achieved in the region climatologically, and so the region is able to support convection at lower sea surface temperatures, and the convection lowers the sea surface temperature. But this is a robust Indian Ocean dipole structure. Then if I looked just in this region of the Central Pacific and compared it to the region around the Maritime Continent, this structure looks like El Nino. While you go farther to the east, the structure over here is more like what you'd expect to see in a La Nina event. This looks like the second EOF of global equatorial sea surface temperature. The first EOF is a strong positive or negative anomaly just in the eastern equatorial Pacific, which represents the more canonical East Pacific standard El Nino structure. But the second EOF, which explains a fraction of the variance, like less than 10% of the variance of or about 10% of the variance of the other one, the leading EOF, is a maximum near, or maximum or minimum near the dateline and a minimum or maximum corresponding at the coast. So that means in that mode, the Central and East Pacific sea surface temperature are anti-correlated. Now, when people often describe Central Pacific El Nino events, they don't look for it being cold here. They just look for it being anomalously warmer here than here. So the El Nino events that they call Central Pacific El Nino are still requiring a Nino 3.4 to be anomalously high. But in this case, Nino 3.4 is closer to climatology. The Central Pacific is warm and the East Pacific is cold, and this is actually what we should consider as a more classic structure, Central Pacific El Nino event, conforming to that second EOF, which I'll often call the Central Pacific ENSO eigenmode. Very few El Nino events throughout their lifetimes sit at one stage or the other for the whole lifetime of the event. Like 1997 began like this. In February and March, Central Pacific was warm, East Pacific was cold, and then over the next months, the signal advanced from west to east and filled the basin. Some other events begin in the Central Basin, expand eastward, and then retract back. 1986, 1987 was an example of that pattern. But it would be, I think, a poor choice to lump this structure in with normal or averaged ENSO neutral conditions. This is not a neutral state. The warm water here will favor rainfall in this region into the winter should that warm water maintain, which holds substantial impact on likely conditions downstream. So there's my no internet service available. My dinosaur hit the saguaro cactus. So we're going to skip the satellite image, which I couldn't reload. And we're looking at the present distribution of outgoing long-wave radiation anomalies around the equatorial band. So 7.5 north to 7.5 south. And this is the CFS reanalysis around the global band. This is the analysis field here up until the black bar, followed by the CFS 4 ensemble member forecast. Obviously, 4 ensemble members isn't really very productive in getting a broader view of what the full ensemble mean might actually look like. But the CFS works that way. They create a false ensemble by collecting ensemble members at different quarters of the day. So they'll get 16 ensemble members for a day based on different start points in the day. So that's how you get the 16-member CFS ensembles. The active convection you see coming around the world here and a little bit still here is associated with the Western Hemisphere circulation phases of the present MJO event, which arrives back in the model over the Indian Ocean over the next few days, and then you see it kind of jump the maritime continent and come back, reform over the Western Pacific. If I look at different ensemble members, you can see the variation between these things. There's obviously fairly low confidence in the precise timing when the signal arrives back over the Pacific Ocean coming up. When it arrives back over the West Pacific, or even the maritime continent phases, this time of year, or coming into October, is the Eastern North America cold phases of the MJO signal this time of the year. Obviously, the association between the MJO and temperature outcomes varies across the seasonal cycle. So we see the active convection come around. The CFS has a slow bias in propagating the signal across the world. One of my hypotheses to explain this slow bias has nothing to do with the convection. It's that the model has a slow bias in the background winds in the subtropical jet region. And the subtropical jet region helps advect eastward the anomalous geopotential height patterns associated with the MJO. So I think the convection drives a ridge on its poleward side. And then on the north side of that ridge anomaly, right next to the subtropical jet stream, the background wind advects that portion of the response to the MJO. It's like a westerly surge on the jet, gets advected eastward by the jet. And then geostrophic adjustment occurs because that on the east side of that new jet max, where the winds are being accelerated by advection, the acceleration is occurring, producing a Coriolis force toward the equator, but that's not balanced by geopotential height anomalies. And so that redistributes mass, drawing mass from north of the jet to south of the jet, building the ridge eastward from its previous location. And this is one mechanism for dynamical propagation of the MJO using the subtropics. Of course, on the return side of the ridge, that's feeding back on the tropical convection. But the CFS has as you go out to longer and longer leads, has a weak bias in the subtropical jet. It drops off in some cases by as much as 50%. These are not trivial anomalies, and they imply that, well, you might remove the model climatology and look at the anomalous flow and use that as a forecast, but the behavior of those anomalies are going to be dramatically changed by the behavior of the model base state. So if the model has a slower background wind, you're going to expect it to propagate those geopotential anomalies eastward more slowly via this mechanism, which would feed back on the tropics. Now, there may also be other mechanisms in the tropical convection that are influencing the propagation of the signal around the world as well as Kelvin wave dynamics in the tropics. But in any case, the arrival of the new convective signal over the West Pacific is likely to occur before the CFS ensemble mean suggests it will occur. So go back to the ensemble mean here. The earliest time the model has it coming in is late October. And that's probably about when I would expect phase 5 or 6 to occur coming around. And we'll look at some model forecasts on the RMM index to get a feel for that coming up. But that's important to get the timing of the favored cold outbreaks potential coming up in October. We may have some synoptic cold before this time transition occurs, but the subseasonal variability favors a cold event this time of the year when the maritime continent and West Pacific MJO comes into place. I'll show you that also a little later. So look at the low-level winds in addition to this robust MJO event. seem to be fairly weak in the low-level westerly winds. So this is 850 winds. Again, around the world, same thing we were looking at before. The westerlies are in the warm colors and the easterly anomalies in the cool colors. And there's a Bay State signal in here, which is favoring easterlies over the Indian Ocean, evolving toward easterlies east of westerlies. And then the Central Pacific and West Pacific has had westerlies, while the East Pacific has had easterlies. And you see the MJO and equatorial Rossby wave signals going back and forth in a zigzag pattern here. But this westerly phase of the MJO event coming around the world, associated with that recent westerly wind burst that we were showing, has an impact on the ocean and is changing conditions back toward a more El Nino-like condition. This is a slower, more eastward evolving signal over the Pacific than usual. It's taking more time in the model over the East Pacific than an average event would do, when there would normally be a more rapid adjustment back to trade winds. This event back here might be changing the low frequency state in a way that favors stronger westerly anomalies or more westerly anomaly occurrences in the Eastern Pacific over the next few months, should the low frequency background state begin to couple up to the changing ocean surface. Trade wind surge here, easterly phase of the MJO co-located with the easterly state of the ENSO condition and the Indian Ocean dipole, favors cooler, drier conditions near the maritime continent overall. Westward moving signal here, associated with equatorial Rossby waves that were broke into the East Pacific region by this MJO event, propagate westward and continue to keep the westerlies going through the easterly phase. If there were no wave like this, if it were just westerlies and easterlies, the easterlies here would undo some of the effect of the westerly winds on the ocean. But this westward moving westerly phase is interfering with the eastward moving easterly phase, resulting in more contributions from the westerlies over the next few weeks, which favors then amplification of El Nino conditions. The upper tropospheric wind has shown the Bay State westerlies over here. Maybe it reforms later on after this MJO goes through. MJO upper tropospheric easterly winds along the equator occur both with Kelvin waves, so in a trough on the equator, but they also occur in ridges approaching the equator, forced by the tropical convection to the west, but then propagating back onto the equator. So these, most of this signal through the Central Pacific here is associated with ridges coming into the equator. And as the ridges come into the equator, the geostrophic adjustment associated with those air masses moving equatorward results in acceleration of easterlies on the equator, and then upward motion in the back side, on the west side of a pair of ridges, like subtropical ridges like this, produces a cooling, which produces a trough anomaly. So there's adiabatic cooling on the back side of ridge pairs. So the ridge pairs are producing acceleration of easterlies on the equator, but then on the back side, upward motion favored reduces the temperature and reduces the geopotential heights, so that then you end up with a relative trough co-located with easterlies, and that becomes the Kelvin wave that comes around behind, associated with the MJO. But this whole process of movement around the world is intrinsically coupled to the extratropics. But in addition to the MJO timescale signal, there's also a low frequency signal in here that seems to be growing over time in the model, which over time would favor the Central and East Pacific to have upper tropospheric easterly winds, which is the normal pattern even within and just east of the tropical convection. But then westerlies farther to the east, where trough anomalies are forced onto the equator by the wave train response to the ENSO convection. So coming around the world here, we have the MJO signal. It comes back over the Indian Ocean again in late October. At the same time, we would say that there's you're seeing kind of simultaneous in the model, simultaneous convection over the Indian Ocean and the Central Pacific, which is kind of interesting. This doesn't project very well onto common indexes of the MJO like the RMM index, because the RMM index uses, or the RMM index uses a pattern that has a wave number 2 structure in convection in OLR anomalies. Not, this would be like wave number 3 or so. Wave number 2 would have active Indian Ocean, suppressed West Pacific. This is active Indian Ocean, active West Central Pacific. Other models, this is the ECMWF product, which shows the westerly wind anomalies associated with this big westerly wind burst, the MJO event coming around right here, forcing westerly winds anomalies over the eastern Pacific. There's an eastward propagating signal in here, and there also seems to be a standing signal in here, something that kind of holds on over time. So the Indian Ocean dipole signal maintains activity there, while ENSO is kind of fighting the eastward moving easterly phase of the MJO over the eastern Pacific. Oh, and I won't be able to look at the actual data here for the velocity potential. The velocity potential will be showing a more robust eastward moving structure here right now. We might be able to see it when we look at the CPC data. I think all that got downloaded. But this is a fairly classic MJO structure for this time of the year. It looks more consistent with MJO events that occur while El Nino signals are growing. So now let's look at the ocean subsurface. This is the most recent PENTAD for the Tau buoy data, temperature cross sections, averaged from 2 south to 2 north. Recall that this average from 2 south to 2 north doesn't necessarily imply that we have all of the buoys at 2 north, the equator, and 2 south. There have been recently, and I can't check right now, but there have been recently some buoys missing, especially on the equator, which will shrink the size of the anomaly because oceanic Kelvin wave anomalies have greater expression on the equator than they do at 2 north and 2 south. So this is the most recent. You've got like a 2 degrees C positive anomaly here. It's not that much bigger than what it was last week when we looked at it, but I am toggling back and forth between early September and the present, and you can see the response to that westerly wind event acting to push the thermocline down and extend eastward the subducted thermocline, producing a warm anomaly that advances eastward. At the same time, you still see this cold anomaly associated with the recent trade wind surge event that happened before this westerly wind burst. The other Tau data, I'm going to show you today time sections, time longitude sections that just show really how abrupt the ocean response to this signal is. So on the left side, we have zonal wind anomalies with the westerly wind anomalies in the warm colors. And the right side is the sea surface temperature anomalies. And we'd seen over the summer this general retraction of the warm anomalies associated with the El Nino event, collapsing back, resulting in removal of the El Nino advisory. But then this westerly wind event has produced a shock and redistribution of the signal back to about where it was in July, before the strongest August retraction occurred. This retraction right here in August is a direct response to this surge in the trade winds right here. And the effect of that surge in the trade winds is then propagated eastward by an oceanic Kelvin wave. Even though there's only slight easterly anomalies here, there's a large cold anomaly just west of the Galapagos Islands, which is a response to these recent trades, but also there's a Kelvin wave propagating this way in response to these anomalous trade winds. This whole pattern, the wave pattern, will continue to propagate eastward, but how far eastward the warm anomalies get depends on the surface winds with which the oceanic Kelvin wave interact as it goes eastward. So if the downwelling Kelvin wave reaches this area at a time when the local winds have easterly anomalies, the result is an attenuation of the wave and a reduction of the surface effects. So this is how you can get a Kelvin wave to go all the way across the basin and not have the ocean change from a Central Pacific El Nino type structure to an East Pacific, more canonical structure. If the winds continue to favor easterly anomaly development in the eastern basin, as the Kelvin waves arrive there, as the downwelling Kelvin waves arrive there, then it will tend to concentrate the biggest warming effect of the approaching downwelling wave in the central basin. But this advance eastward here is huge. And we want to now look at it in terms of the temperature, 20-degree isotherm depth. So the 20-degree isotherm is a great proxy in the tropics for the depth of the thermocline. So we're saying that roughly the thermocline here is about 15 meters anomalously deep. And that's not a really big signal in comparison with past events. I would bring up some in 1997 or even 2014 and 2015 that are far larger than this signal. But this is changing the story of what we've been seeing for the last several months, because there really wasn't a substantial buildup of positive anomalies. It's at the end of an El Nino event, oftentimes warm water volume is drained out to the east and then up and down the west coast of the Americas. And we've been seeing that a trend toward warm water volume concentrated in the eastern basin with comparatively little warm water volume in the central basin. And some people might suggest that warm water volume is something that takes a long time to accumulate, because technically it's a gradual process of radiative balance and the effects of wind and other temperature feedbacks on the ocean surface. Warm water tends to accumulate over time in the western basin because the background trade winds over the full ocean are in that direction. So just gradually wind stress is building up the warm water volume back there. But that's not the only way that the equatorial region can gain warm water volume. If there's warm water volume already existing off the equator, then substantial westerly wind events in the western basin and the central basin can migrate that warm water volume onto the equator. So you can look at warm water volume charts from the CPC and see large changes over time. There's oftentimes a gradual buildup during La Nina events of warm water in the western basin, and that's the kind of discharge-recharge signal going on, that one aspect of a mechanism that drives the development of El Nino events. But in addition to that, we can have even shallow surface warm water in the subtropics, and a strong westerly wind event that by accelerating the water and the ocean responding to the rotation of the Earth, accelerates the water toward the equator and pushes the thermocline down. So that mechanism can create warm water volume on the equator much faster than the gradual thermodynamic feedbacks can do. You're actually just transporting water from a place where it already exists. So this is a big change over what we've seen in recent months. While this looked more like what you'd see at the end of an El Nino event, this looks more like what you'd expect to see early in an El Nino event. And there's a possibility that this continues to develop. Of course, at the same time, we could miss a westerly wind event when an MJO goes by this fall. Say some tropical cyclone recurvature causes a change in the mid-latitude circulation, which then reverses the MJO state in the tropics by propagating waves into breaking waves into the tropics, initiating upward and downward motion in different areas than it was at the time it occurred. The result is a resetting of the MJO condition in a different location, and if it happens to skip a westerly phase over the Pacific because of something like this, so that you get more like a doubled up, you get an easterly phase and then a new easterly phase. In that case, the net effect on the ocean in moving conditions away from warm conditions would occur. So there's always risk that a simple weather event can change the trajectory of the subseasonal pattern, which can then change the trajectory of ENSO itself. Even a tropical cyclone, rightly timed, well timed, can produce a change in ENSO conditions in the coming months. There are even direct effects of tropical cyclones on the ocean that can feed back on oceanic Kelvin wave formation events. But these are frequently associated with MJO signals anyway, so there's a statistical association with a subseasonal signal usually when it happens, but not always. Okay, so I think all the data for the CPC sites are loaded right now. We're looking at 5 north of 5 south, and there's coming into the summer, the El Nino convection there that kind of weakened, faded out. A lot of times what's really happening in the summer months is the convection is moving off the equator. So it's favoring a region that doesn't now project onto equatorial westerly wind anomalies, and so there's oftentimes a weakness in ENSO development signals unless the equatorial sea surface temperature can maintain high. That takes quite a warm anomaly to keep it going. So if you look at 1997, the summertime, that was one year where equatorial convection continued all the way through the summer. 2002, equatorial convection continued through the summer as well, but it's not really typical. There's usually a breakdown because the seasonal cycle produces a stronger warming north of the equator, northwest Pacific subtropics. We have a region of suppressed convection that has a stationary component and a subseasonal component, and it's on the strong side in comparison with what we've seen since midsummer. So this suggests that we both have a bay state signal here, suppressing convection near the maritime continent, and a propagating signal of suppressed convection that's now migrating to the West Pacific. We also have active convection located over the Western Indian Ocean, and it seems to have a stationary component, and possibly, it's not so obvious, a propagating component here as well. But we know in the circulation signal that there is indeed a propagating component. Let's go to, I want to see 850. Yeah. So the 850 wind signal is showing a propagating component here where you've got a clump of westerly wind events, Western Pacific, but now the westerly anomalies are located over the eastern basin. It's consistent with the data we saw earlier from the CFS and the WSI product. The upper tropospheric wind pattern has an interesting symmetry right now across the equator. Look at that. Beautiful westerly jet anomalies, subtropical jet anomalies, north and south of equator reflected from near Hawaii and to the south. And there's this wave train coming in across the South Atlantic, Southeast Pacific, and Indian Ocean, which is enhancing the upper tropospheric easterly winds in this area, which is a precursor for development of Indian Ocean MJO signals. But this has a signal that's left behind in the central Pacific that is probably associated with adjusting ENSO in addition. And so you can't look at this signal and diagnose a pure MJO structure, and it's not wholly consistent with what you'd expect if it were just the MJO alone as the dominant signal. I mentioned the velocity potential. So this is the 200 hectopascal velocity potential signal. There's been a signal coming around the world. Didn't really go away, but there was a period of time with a lot more noise going on in July and August especially. But there seems to be an eastward moving signal in here that's emerging even relative to the time mean, suggesting a signal moving right now across the Western Hemisphere and toward the Indian Ocean. It's consistent with the model forecasts for an Indian Ocean event coming up, but none of the models are producing a really big, well-organized Indian Ocean event. It's more difficult to get a strong Indian Ocean event during a substantial Indian Ocean dipole signal, because the dipole is enhancing one part of the basin and weakening the other part, so suppressing convection in the other part, while an MJO will typically excite the whole Indian basin at the same time. And so there's a countering signal in the base state that's reducing the ability of MJO convective signals to propagate across the eastern Indian Ocean and the maritime continent. But that doesn't mean that circulation signals won't go and translate the signals around, and that's why the models are able to still produce this convection over the Indian Ocean, gap convection over the West Pacific again. So there's a substantial subseasonal or a substantial background state modulation of the subseasonal signal. 850 and 200 millibar velocity potential signals are pretty much consistent with each other right now, well in phase, and this is just barely beginning to show the heat content in the ocean, just beginning to show the oceanic Kelvin wave signal that we're watching now. It's not really impressive in comparison to what we had before. So again, as far as ENSO goes coming into the season, there's a wide range of different possibilities. The event could continue to fade out, or it could amplify into the coming winter and spring. So here are the model RMM index forecasts from the CPC site. The GFS. The GFS has a bias toward favoring wave breaking, maintaining wave breaking over the Western Hemisphere, dropping ridges onto the equatorial Atlantic region. And you'll see this showing up in the upper tropospheric and then responding in the lower tropospheric winds. So the GFS is typically favored. This is the GEFS, so it's an older version of the GFS that favors the signal to just kind of sit around over here. So this is normal GFS. This is a bias-corrected version, and the bias-corrected version actually says it stretches the signal to the right, but that gives a perception of it just kind of sticking around here in phases 8 and 1. If you look at the ECMWF, well, it seems to be doing the same thing. Bias correction moves it to the right. This bias correction is not bias correction of the indexes. This is bias correction of the data fields. And it's not based on a long-term climatology of bias. It's based on the recent months. So how have the recent what have the recent months' errors clustered like? And so it's basically a suggestion that the recent errors are representative of the bias, which has some correlation to actual bias, but it's not actual bias. You would to assess the actual bias of the model, you would want a long climatology under the same predictor basis. So a little bit different. The ECMWF wants to go a little farther east, but this is the ECMWF climate model, and this was, I don't know if it updated today. This is 24th of September, so this is the previous run. I suspect the newest run will be similar. What we have is an eastward moving signal in the circulation. I was showing that to you in the winds. The models are showing the signal moving around the world. But computation of the RMM index requires removal of the low frequency signal first. But the low frequency signal is changing. So the recent time mean, say over the last 120 days, is not an appropriate time mean for removing the signal today. Anytime the base state is moving, you're not going to... and so what the superposition of the mean state and the subseasonal state results in some movement in the index. Looks like this. Maybe it's favoring this area on the lower left. Carl Schreck has some good data that I recommend you play with on his SIX website that breaks down into low and high frequency. I can't show it today because of the internet issue. Nevertheless, the model shows propagation of the signal forward, but look how far it is spread. So there are some ensemble members at the end of 30 days. They're still in phase 3. Other ensemble members that may even be in phase 1. Strung all the way out across 5, 6, 7. So there's enormous spread in where the model places the subseasonal condition by the end of October. But it's also suggesting, even though the amplitude may look small, it's suggesting to me that there is a substantial subseasonal signal going on, even though the model has a lot of variance in where it places it. So it suggests that if you have some way of better predicting the most likely speed of the event coming around, that you could choose which ensemble members are most likely to reflect those outcomes. And in this case, I think the most likely outcome is that the Pacific phases reemerge in the last part of October, and those are associated with a particular set of favored outcomes. So we've seen the subseasonal variability favoring a 200 hectopascal geopotential pattern that looks like this, and we've had some verification of this structure lately. Going forward into October, that starts to break down, first with intrusion of a cutoff trough that might get back into the northeastern U.S. And then going forward, that expands westward and then results in a full eastern North America trough signal in late October. And this is the most likely outcome if the timing of the MJO arrival of convection is in the last week, early in the last week of October. So you see it beginning to set up here after the 20th, and then growing, and then a northward moving signal left behind. Would suggest that there, given that timing, a cold period in the end of July. In October, sorry. I think I must be on some kind of something today. I don't know. Looks good though. Cold signal coming up end of October into November. pattern over Europe is interesting too. The favored subseasonal pattern. This is subseasonal only. This doesn't include any low frequency forcing. Has a block mid-October over the North Atlantic, which then evolves to a European ridge pattern, like that. For those of you who might be interested in wind forecasting for Europe. Again, this is just what the MJO by itself would do.
What does the phase one mean?
What's that? Question from the audience.
There's a phase one. On the upper left, say.
Oh, phase one. So it's just the website. I took the website from an earlier site, this one, that covers phases, and I just didn't delete the text. So I need to go back and change that. It's something. It shouldn't be there.
Okay.
So there are no phases in this thing. What it's doing is taking the overall structure and recent evolution of the MJO and OLR anomalies in the tropics only, and then projecting that forward using the method of seasonally varying regression slope coefficients to produce what the seasonal cycle that time of the year at the validation most favor given the initial conditions. It's okay. I cannot show the model signal, but I can, because it won't let me renew and zoom in on anything because of the internet issue. But I will finish out by showing what this, oh dear, maybe I won't. Maybe I won't. It looks quite like this structure if I look at evolution toward phases 5 and 6 coming at the end of October. So phases 5 and 6 come the end of October, favor the development of that eastern U.S. trough signature. This time of year, if my recollection is correct, it's all on that website for anyone interested in looking at. I'll bring it back up so you can, let's see, this one. It's this one right here. So you should be able to pause. If you're watching the video, you should be able to pause and look at this. This is the seasonal average expectation values of RMM index associated signals in the global 200 hectopascal circulation, and the favored zonal meridional structure of the OLR anomalies. So bottom line this time is we're in a period of amplification of El Nino conditions. We don't know how long that's going to last, and subseasonal signals presently moving back with convection toward the Indian Ocean, and probably getting back toward the eastern maritime continent and West Pacific phases in the last week of October, favoring a transition toward a cold signal, which, given how warm it's been here, so in the last several weeks, it could be quite a shock in some of the markets to see the development of the favored cold signal. Thank you.